Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the Robert Bosch Center for Cyber Physical Systems at IISc. Today's talk is by Professor Krishna Narayanan, and he will be speaking on connections between unsourced multiple access and sparse recovery. Professor Krishna Narayanan is the Eric D. Rubin Professor in the Electrical and Computer Engineering Department at Texas A&M University. His recent research interests have been in massive multiple access for IoT, coded distributed computing, machine learning for joint source channel coding, and graph neural networks. He is a fellow of IEEE and recently received the 2020 Best Paper Award in Data Storage from IEEE Communications Society. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Professor or type them in the chat box and we'll moderate it with him. Over to you, Professor.
Well, thank you very much. Thank you very much for the introduction and also for the invitation to give a talk at this seminar series. It's always very exciting to talk to the people at IISc and beyond. The only disappointing part is that I'm not in person. I would have loved to be in person to give the talk. So before I go on with the talk, please feel free to stop me at any time and ask questions. I don't really have. There is something in the chat. Okay. Yeah, so please feel free to stop me and ask questions. I have a few important points I would like to make, but I can always plan my talk such that we can finish in 50 minutes and still answer the questions. So this is some work that I've been doing with several of my colleagues at Texas A&M University over the past few years. And I thought I would share some of what I've learned about connections between multiple access and sparse recovery. The talk is a little bit long, so I tried to organize this in 4 parts. So in part 1, what I will try to do is to simply introduce a few sparse signal recovery problems, perhaps even broadly called as compressed sensing problems. I'll try to summarize the state of the art in what we know about constructing sensing matrices for these problems and recovery algorithms. And I will try to make a case that we need new algorithms as we go to larger and larger dimensions. And I will try to discuss some applications where there is a need to go to large dimensions. And somewhat unrelated to part 1, I will talk about unsourced random access in part 2. And this is a field that has evolved in the last maybe 5 to 10 years. And the main part of the talk is in part 3, where we try to show that, these two problems are really the same problems. It's just that the first one seems to be a signal processing view of the problem, whereas the second approach seems to be more of a communication theoretic or a coding theoretic view of the problem. And in part 4, I will try to show that this connection can be used, thinking of this problem as a communication theory problem can be used to design good schemes for large scale sparse recovery problems. And I know that, like I said, there are 4 different parts. Some things seems a little bit unconnected to the rest. So I want to tell you right away that there are 4 main points I want to make. The first point is that unsourced random access is the same problem as an approximate support recovery problem. There is a need for low complexity algorithms for approximate support recovery, and that taking a communication theoretic or coding theoretic view of the problem can help us design good sensing matrices and low complexity algorithms. And this has potential for some large scale compressed sensing problems, including multiple measurement vector problems, so on and so forth. So I wanted to tell you this right away because if we go through the talk and at the end of it, if these things are not clear, please feel free to stop me and I will try to see where this should have been clear. Okay, so let's begin with an introduction to a compressed sensing problem. So in a compressed sensing problem, you have a k sparse vector, we'll call that S, of dimension n. And we get to observe noisy linear combinations of this vector. So we get measurements of the form y is a times s plus z. A is a m by n matrix. Z is typically Gaussian random noise. And y is our vector of observations. So we're going to use m to denote the number of observations and n to denote the dimension of the vector. So typically we want m to be much smaller than n, and the problem is to recover s given y, right? There are many flavors of compressed sensing problems. In the particular versions we are interested in, we get to choose the sensing matrix A. The sensing matrix is under our control, so we get to choose a sensing matrix A, and we observe A times S plus Z, and we want to recover S from Y. Okay. Now, a few parameters that are typically of interest in this problem is first the undersampling ratio. So how small can M be in relation to N? So we'll denote that by rho. So rho will be M over N. And the other important parameter is the sparsity of the signal itself, right? So it's the ratio of the number of non-zero entries in S to the dimension of S. And typically we're interested in two regimes. In one, we would say that the sparsity is what we call as the linear regime, where the sparsity K is order of N, so some fraction of N, and we'll use kappa to denote the fraction. We are sometimes also interested in the sublinear regime. So in the sublinear regime, things are very sparse. So K is of the order of N to the alpha, where alpha is some exponent less than 1. Okay. And like I said, there are many versions of the problem. When I say versions, I mean people have studied different performance measures, how many measurements you need for a given sparsity under various reconstruction errors, so on and so forth. Now, one particular version of this that I'm interested in is in what is called as approximate support recovery. And so here we care only about recovering the non-zero coefficients in S, or the support of S, right? And so there is this work by Galen Reeves and Michael Gaspar back in 2012, where they derived a rate distortion bound for this problem. So what they basically did was to derive the number of measurements, or the ratio of the number of measurements to the dimension that you require if you want to reconstruct S up to a certain distortion measure. And the distortion is a fairly natural measure, which is to say, I have this sparse vector S. If you give me the reconstruction S hat, how many misdetections do I have and how many false alarms do I have? And I take the sum of both of them. So in a sense, it's Hamming distortion between S hat and S. And what they were able to do is to quantify this distortion rate trade-off. So for example, you get some plot like this. So if you look at the plot, the y-axis is sampling rate, and the x-axis is SNR. And in this plot, the sparsity, so this is in the linear regime, and the sparsity is set to something very small, 10 to the minus 4. And we want to reconstruct S up to a distortion of, let's say, 5%. And then the figure here shows, what is achievable and what is not achievable in terms of the sampling ratio. And they were also able to quantify this for a few specific algorithms, recovery algorithms, and sensing matrices. So typically, in this case, the sensing matrices are randomly chosen, random Gaussian sensing matrices. And then you have these different decoding algorithms, and you can see that, simple decoding algorithms like just forming a linear MMSE estimate require very large sampling rates, whereas approximate message passing and some kind of more fancy decoding algorithms give you better sampling rate for the same distortion. So this is what I'm going to sort of use as a benchmark. So when we design our schemes, I want to kind of put a point on this plot to see how good the schemes that we design are, for example. Okay. Now, there is also another line of work where you ask not for approximate reconstruction, but you ask for the reconstruction to be exact asymptotically. So you say that as the dimension n becomes large, I want the reconstruction error to go to 0. And the main result in this case is that you require roughly k log n over k measurements. Again, k is the number of non-zero elements in S, n is the dimension of the vector. So you require roughly k log n over k measurements. And just keep this quantity in mind, because I'm going to show later on that some of the schemes that we design are order optimal. Okay. All right. So there has been a lot of work in the last 15 years or so, maybe 20 years, on constructing this A matrix, which we call as the sensing matrix, and also on recovery algorithms. So I'm not an expert at either of these two, but what I understand about the state of the art in this is that typically, there are a lot of constructions. Random constructions are typically used for proofs, and also when the dimensions are small. People have looked at more deterministic constructions, such as picking rows from a DFT matrix or a Hadamard matrix, or sensing matrices based on Reed-Muller codes, sensing matrices based on low density parity check codes, for example. And in terms of recovery algorithms, I would say there have been largely two classes of recovery algorithms. The first set of recovery algorithms, you can think of them as convex optimization based solvers. So it turns out that you can think of this reconstruction problem as a regularized least squares problem. So you try to find the S, or I think I switched to X here, which minimizes a weighted sum of the 2 norm of y minus a times x, and you add a penalty term, which is the L1 norm of x. And there are many solvers. Again, I'm not an expert on these things, but the main point I want to make about this is this. These solvers are computationally intense. So typically, these convex optimization based solvers can be implemented for maybe dimensions which are of the order of 10,000s to maybe 50,000, a few 10,000s. And then it becomes fairly complicated beyond that. There has also been this line of work where iterative thresholding based solvers have been used. So for example, approximate message passing or learned soft thresholding based algorithms. And these are less complex than the convex optimization based algorithms. You can push the limit of n to maybe a few 100,000, maybe up to 1,000, things like this. And I think this is pretty much the state of the art. But what I'm interested in this talk is in n being even larger than this. And now we get into a situation where the complexity of these solvers is fairly large, and we want to look for algorithms where the complexity is scaling with n sublinearly. So even linear scaling is pretty large. And one thing that's important is when you try to design algorithms that are computationally efficient, it goes hand in hand with the construction of the sensing matrix. So typically what you want to do is you want to put some kind of structure on the sensing matrix that makes it easy for you to design an algorithm which has low complexity. And so this is basically what I want to talk about. And so you might ask, so where are some applications where you require large values of n? And so I'm going to try to give you a few of them. So the first one is a classic problem in theoretical computer science. This is called as the heavy hitters problem. And since this is a networking seminar series, so perhaps you will appreciate this. So think about a router in a network. You have packets flowing through a router in the network, and the router wants to keep count of the IP addresses to which packets are flowing. Now, typically what's going to happen in this situation is that you are going to have a few IP addresses to which most of the traffic is destined, right? So we call these as the heavy hitters. Now, if you naively think about the total possible number of IP addresses, that's huge. Could be 2 to the 64, but out of which only a very small number of them are really getting a lot of counts, right? So if you think about maintaining a dictionary, or you are maintaining some kind of a data structure which will keep how many packets are flowing to which destinations, naively doing this will require a very large memory. However, since only a small number of them are going to be heavy hitters, there has been a lot of interest in theoretical computer science in designing data structures which will keep only the top k entries. And now when you think about this problem, this more or less is a compressed sensing problem with a very large dimension, right? And it's kind of very nice, because one way to do this is, what you can do is every time a packet flows through your network. So for example, think of a vector with indices going from 1 to 2 to the 64. If I get my index of the packet to be 10, now what I can do is I take a sensing matrix, I take the 10th column of this sensing matrix, and then I add that to a running sketch that I have. So every time a packet flows, I simply add the corresponding column to my sketch. Now, after a certain number of packets have flown through my router, essentially what I have at that point is this matrix A times a histogram vector, which tells you how many packets were destined for which IP address, right? So again, this is this 64 is supposed to be in the exponent. So this, you can see, is a compressed sensing problem with a very large dimension. And there has been a lot of work in theoretical computer science trying to solve this problem. I'll talk about this towards the end again. So here is another problem in wireless networks. So this is the problem of neighbor discovery in wireless networks. So suppose you have a large number of users in a network, out of which, let's say, k users are active, and you want to identify which users are active. And one way to do this is for each one of the users to send a signature sequence at the beginning of the transmission. And in this case, the base station will receive a sum of the transmitted signature sequences plus some noise. And of course, what the base station then wants to do is which set of k users transmitted their signature sequences. So if you think of a matrix whose columns are the different sensing or the different signature sequences, then essentially what you get to observe is A times S plus Z, where S is a vector, is a 0, 1 vector, which tells you which users are active and which users have not been active. Now, this problem, now, if you think about identifying users based on their MAC address, for example, then again, the space of possible MAC addresses is huge, right? You could have 2 to the 48 possible MAC addresses. And you may have 100 users who are active in your network. So then you're trying to identify 100 users out of 2 to the 48 possible MAC addresses. So again, this is a very sparse problem in very large dimensions. Now, the multiple antenna version of the same problem is also very interesting. And so in this version, instead of having one antenna in the base station, you just have multiple antennas in the base station. And since you have multiple antennas in the base station, you can think of one column of the received vector corresponding to each antenna, and you can try to put all your received observations into a matrix. And in this case, the structure you will have is you have a sensing matrix A, you have a diagonal matrix. The diagonal entries in the matrix are 0, 1 values. It's 1 if a particular user is active, and it's 0 if the user is not active. And you have a matrix where the ith row of that matrix is the fading coefficient corresponding to the ith transmission. I'm sorry, to the ith link between user I and the base station, right? So this is just the multiple antenna version of the single antenna version. However, from a compressed sensing point of view, this is more involved. And I know that a couple of weeks back, Professor Sri Krishna Bhashyam talked about this problem. Now, there are, in my view, two slightly different versions of the problem. So in the problem he talked about, for example, n is of the order of a few thousands. So that typically makes sense if you have a protocol where you somehow have narrowed down the number of users to a few thousand users, and within those few thousand users, you want to identify who's active. But if you have not done the first part, which means you have to identify them based on their MAC addresses, then n is really very large. Then n could potentially be 2 to the 48. Now, of course, these days, none of the talks can happen without some form of machine learning. So another problem where this seems to make sense is in what people call as over-the-air federated learning. So the idea here is that you have a wireless network and you have several users in the network who are all trying to train some form of a machine learning model. So perhaps a neural network model, but with very large number of parameters. These days, state-of-the-art machine learning models have millions of parameters, if not more, hundreds of millions. And what they want to do typically is to send their gradient. So they don't want to reveal the data that they have. So they want to do the training on their machine, but they want to aggregate all the gradient vectors so that everybody has the same gradient after each stage of training. So in this case, each user wants to send their gradient. So this is a user wants to send its gradient to a base station. And typically what happens is these gradients are sparsified. So even though the gradient is a very large dimension, it may be that the gradient itself is very sparse naturally, or even when it's not entirely sparse, you may want to update only some components of the gradient. This acts as a regularizer. And in this case, essentially what you have is a compressed sensing problem, because you have a sparse vector that you want to communicate, but you have many distributed users who want to do the same thing. Now, if they're all synchronized, then one way to do this is for each user to multiply their sparse vector by a matrix A and then transmit them. Now, the receiver will receive a sum of A times each one of the vectors, S1, S2, S3, so on and so forth. And if you are in the right sparsity regime, even the sum of these vectors may be sparse. So essentially, you end up having to recover A times the sum of these gradients. And interestingly, in this problem, the base station usually is interested only in the average of the gradients. The base station usually does not care about S1, S2, S3 individually. It cares only about the averages of S1, S2, and S3. So it seems like a perfect fit to the compressed sensing problem, right? So these are all different problems where we're interested in designing some kind of low complexity compressed sensing algorithm. And like I said before, I'm going to try to show that thinking of these problems as multiple access problems helps you design compressed sensing problems. So I'm going to talk about unsourced multiple access. So multiple access is an old problem in information theory, old in the sense it's been studied for a very long time. So the typical problems that have been studied in information theory are where you have a small number of users, or typically you have k users in a network, and each one of them gets to use the channel n times. So in classic information theory, you fix the number of users, and then you let n become very large. N is the length of your code words. And then, you ask for the capacity region of the multiple access channel, or you ask, what rate everybody can get to transmit. However, okay, so before I go, so typically when we talk about a multiple access channel in communication theory, there are a few assumptions that we sweep under the rug. So one of the assumptions is that typically we assume that the base station or the decoder has somehow already obtained the identity of the users. So what I mean by that is, each user may use a different set of parameters for their code. So they will encode their information. Let's say user 1 has message W1, they encode their information with an encoder E1. Now E1 may use some parameters, maybe spreading sequences, or maybe time slots at which they transmit, maybe frequency slots at which they transmit. Now these parameters are typically chosen by the base station in order to manage interference. Right? So the identity of the user has somehow been already conveyed to the base station. And based on these identities, you can allocate resources to the users. But this sort of paradigm does not really work for things like the Internet of Things, where we are interested in the following multiple access problem. Right? We have a very large number of users in a network, out of which K users are active at any given time. And you can think of some kind of a MAC protocol like this. So each one of these users has a small packet to transmit, and the base station periodically sends a beacon. If a user has information to transmit, you listen to the beacon, you estimate the channel, and then there is a phase where you say that I have information to transmit. So this is like the user identification or the neighbor discovery problem that we just talked about, right? Now, at that point, the base station has learned how many users or who in the network wants to transmit. But the users themselves do not know who else is there in the network. And the base station says, okay, 100 people want to transmit information. So here is the length of the frame over which you are going to transmit your information. So we want to focus on what happens within that part of the transmission. So the base station knows the number of users who want to transmit, but the users themselves do not know who else wants to transmit, and therefore they cannot pick the parameters of their code in any kind of coordinated fashion. So you have to work in a paradigm that looks like this. Each person has to take their message and they have to encode it with exactly the same encoder. And they all have to transmit their message. The base station now, of course, tries to recover the messages. And typically what is assumed is that the user's message itself has the user's identity and the payload together. So the job of the decoder or the receiver in this case is simply to get the set of messages. It doesn't really care about which device is actually transmitting which message. It cares only about getting the set of messages, because either the user identity is embedded into the message, or you probably don't even care about the user identity in some problems. Okay, so these are the two different twists from classical multiple access in unsourced multiple access. The two twists are this. First thing is everybody is acting in an uncoordinated way, and as a result, everybody is forced to use exactly the same encoder. Number two, when you do the decoding, you only care about getting the set of messages. And typically, the error metric that you use is also a per user error metric. You say that I'm interested in making sure that I recover every user with 95% probability, for example, right? Instead of saying that my probability of error is the probability that I get at least 1% wrong. So if you think about this, okay, so that is basically a description of the unsourced random access problem. Now, this has become popular in the last, I would say, 5 to 10 years, largely motivated by applications in Internet of Things and what they call as grant-free communication. Have any questions at this point? Okay. So here's the main point of the talk. Okay. So the main point of the talk is these two problems are exactly the same. Okay. To see that, let's first think about the multiple access problem and think about the case when each person has a small packet to transmit. So I have a bunch of bits to transmit. One way to think about this is to say, so maybe let's say I have B bits of information to transmit. Or maybe I think I'm using W. So W bits of information to transmit. We can think of these bits as an index between 1 and 2 to the W, right? And then since every user is forced to use exactly the same encoding, what we can do is we can think of a sensing matrix or a code book where the ith column in the sensing matrix corresponds to the code word for the ith index. So if I want to transmit the ith index, I pick the ith column from this sensing matrix or code book, and then I transmit. So if you think about this, then the size of this code book is M, which is the number of times you use the channel. I'm sorry, maybe I should switch to M. M is the number of times you use the channel times 2 to the W, where 2 to the W is the total number of possible indices. So you can see this is actually just like a compressed sensing problem with small m and very large number of columns, right? Now, each user, of course, does this independently. So then what you get to observe is simply the sum of k of these columns plus some noise. And since we care only about decoding the users up to a permutation, essentially what we are asking is that we identify which columns have been active. It is exactly the same as the support recovery problem in compressed sensing, right? Now, we can also think of the other way, and this is perhaps the more important way I want you to think about it for the rest of the talk. If I have a compressed sensing problem, let's say I have a signal S, which is k sparse of dimension n. One way to do encoding or doing a compressed sensing measurements for this is to do the following. You take the non-zero indices in your vector S, convert the indices to a binary representation. And now if the dimension of S is n, my binary representation is going to have log n bits. And now if you can encode this binary index or the binary representation of the index with an encoder, with an identical encoder, and then you sum them up and then you add noise to it, essentially you get the same thing as noisy linear observations of a linear measurements of S, right? This is basically the connection that I want to explore further. But this problem itself is nothing but this unsourced random access problem. So what I'm trying to say is this: if I know how to design a good multiple access scheme, if I know how to design a good encoder for here and a good decoder for here, essentially I have constructed a compressed sensing scheme and a recovery algorithm to solve the compressed sensing problem. The key thing is this: here we are dealing with communicating log n bits. But of course, this corresponds to a dimension of n. And the point is, if n is large, communicating log n bits is just the same as communicating a short packet in an unsourced random access problem. So hopefully, if we can do something here, then this means something for the something nice for the compressed sensing problem. Do you have any questions at this point? I feel like this is the main connection between the two that I want to explore further.
Professor, I have a question.
Yeah.
So here you mentioned that you're taking the indices of the support of this vector, and then you're basically converting that into a message and transmitting it. But what about the magnitude of the entries that you wish to of these entries that you wish to recover?
Okay,
What do you
okay,
do for
very
this?
good question. So notice that these SKs here, so the SKs are the actual values, and
Okay.
you can think of SKs as fading coefficients. So think
Sure.
of this as a multiple access channel, but not as a simply a Gaussian multiple access channel, but as a Gaussian multiple access channel with fading.
Fading. Okay.
But so the received model has the non-zero values. However, our interest is only in recovering the support.
Support. Okay. Okay. All right.
Good question. So is the connection clear?
Yeah. Yeah. I understood. Thank you.
Okay. All right. So for the rest of the talk, I'm going to show how we can construct a good code for this channel, and then I will come back to showing why it is a good, give you some results for some few compress sensing problems. So there has been a lot of work in the last few years in trying to build codes for this unsourced multiple access channel. I'm not going to go through the details of all this. The point I want to make from this is this. Each one of these codes can be ported into a compress sensing problem and into a sensing matrix and a recovery algorithm for the compress sensing problem. And hopefully this makes some improvement into the design of low complexity sensing algorithms. So quite interestingly also, the theoretical benchmarks for this unsourced multiple access problem was done by Yuri Polyansky, who computed some finite length bounds on the signal to noise ratio that you might need if you want this many users, and if this is the number of times you can use the channel. So if you really take his work and you let n become large, you get exactly the same result as Reeves and Gaspar's rate distortion limit for the approximate support recovery problem. So is one more thing that tells you that these two problems are exactly the same. Now, the connection between compress sensing and multiple access is not new, but certainly not new by any means. And there is a very, very rich, there have been a lot of connections. I want to point out a few. So to the best of my knowledge, the earliest one that I know goes back to 1985 from Jack Wolf, where he wrote this nice paper called Born Again Group Testing. So group testing is a version of a sparse recovery problem. Unfortunately, I did not really talk much about that version itself, but he realized that this should be thought of as a multiple access problem back in 1985. And then there has been a lot of work in the multiple access community on the construction of what you call as T disjunctive code. So, the idea there being if T people were to talk at the same time and you had a binary adder channel, would you be able to separate out the T users? And clearly you can see this is fairly related to compress sensing. And I think Chandramurthy has a recent paper where he explicitly even makes construction of sensing matrices based on these disjunctive codes. Now, there's also a lot of work on thinking about this from the perspective of spreading sequence design for CDMA. The one big difference between CDMA and what we are doing, of course, is that in CDMA, like I said, typically a base station will have the ability to assign spreading sequences to users. Instead, here you are forced for the users to somehow randomly pick these sequences. So there's also work by Bhaskar Rao on deriving limits for approximate sparse recovery, thinking of this as a multiple access problem. On the recovery algorithm side, there has been a lot of connections between multi-user detection and compress sensing recovery algorithms, going back to the CDMA large system analysis and its connection to message passing by Tanaka, David Shea, and Montanari. More recently, using approximate message passing and multi-user connection by Bayati and Montanari. There have been attempts at using sparsity inside multi-user detection. And I know that Chandra has been working on sparse Bayesian learning in the context of multi-user detection. I think 2 weeks back, Sri Krishna gave a talk on using machine learning for solving the neighbor discovery problem, which is, again, in my opinion, a very nice problem that connects both compressed sensing and multiple access. But one thing I would say is this: I feel that most of these algorithms typically have taken the viewpoint of using compressed sensing algorithms for improving multiple access. And I want to, for the rest of the time, talk about using something that comes from multiple access in compressed sensing. Okay, so this is the last part of my talk. This is also the new part, and I'll try. This is a little bit dense. I will try to do my best job. Please stop me and ask me if you have any questions. So do I have around 15 minutes? Is that what I have?
Yeah, Krishna, go ahead, please.
Okay. So I'm going to describe a scheme for solving the multiple access problem. And this is more or less inspired almost entirely by thinking of this as a communication problem. Okay. So the idea is to do something like this. So you look at this problem and you say, okay, look, this is just a multiple access problem. Let's do something similar to CDMA and use the right kind of codes, right kind of multi-user detectors. Let's try to solve this problem. And then you realize quickly that it's not exactly CDMA, but CDMA can be changed to fit this problem. So the way we do the encoding, it works like this. You take the message and you split the message into two parts. There is one part which is called M sub C, and there is another part which I'm going to call as M sub S. S stands for signature sequence, C stands for code. So what you do is you take one part of it, the MS part, and then you pick a signature sequence from a master set of signature sequences. Okay, so I have a signature sequence set. The signature sequence set has 2 to the B sub S signature sequences. I'm going to pick one of these signature sequences based on the message that I have to send. Now notice that this typically does not happen in CDMA. In CDMA, a user is given a spreading sequence by the base station, but here you are picking the spreading sequence based on your message. Then you take the other part, M sub C, you encode it with some code, could be a polar code, could be a LDPC code. I'm going to stick to polar codes for this talk, but it really could be any of these codes. And then you get a code word C. Code word is mapped to BPSK, let's say. And then the coded bits are spread by the spreading sequence that you chose in the first part. And that's basically what is transmitted. And the main difference again between CDMA and this is the following. The thing is this: here we have a very large number of users in the network, out of which a small number of them are active at any time. Now, if you naively do CDMA, you would end up using spreading sequences that are very long to try to minimize interference between everybody in your network, right? But this turns out to be really bad because at any point in time, only a small number of them are active. So what we do is to let each user randomly pick a spreading sequence from this master set, but the size of the master set is much, much smaller than the total number of users in the network. Okay, so this is a major difference. And then if you think about what happens from the perspective of each spreading sequence, right? So out of these 2 to the BS spreading sequences, K of them have been chosen. Now the decoder does not know which K have been chosen, right? So the users have chosen K of them, and then they have spread their coded sequence using this spreading sequence. But if you think about it from the perspective of the spreading sequences, if you think about it from the perspective of all the possible spreading sequences, it's as though you take sequence 1. If there are users who chose those spreading sequences, maybe multiple of them choose the same spreading sequence too, because they're randomly choosing their spreading sequence, right? So then essentially what it amounts to is taking the code words of all those users who chose sequence 1, sum them, and then spread it by this spreading sequence, and then you add all of them, right? Now, if that spreading sequence was not chosen, then clearly you get 0 there, so that does not participate. But if it is chosen, then it's just multiplied by some code word, and then you get to observe the sum of all of this. So if you look at what you receive, so you're going to receive, let me just go back here. So the length of the code word that is transmitted is NC times NS, right? NC is the length of the code word from the polar code. NS is the length of the spreading sequence. And what you transmit is NC times NS, is of length NC times NS. So if you look at the received signal of length NC times NS, you can split that into blocks of length n sub s, one corresponding to each coded bit. So each block here corresponds to the received signal for one coded bit. Now you can arrange this into a matrix, right? So you arrange this into a matrix such that the ith column of y corresponds to the ith coded bit. Then in the matrix representation, you can see that you have this matrix S. S is a matrix where each column of S is one of the spreading sequences in the master set. It's one of the sequences that are active. So you take S and you think only of those sequences that are active. Now each column of V corresponds to one bit that is transmitted by all the users. So V is of dimension K by N sub C. K is the number of users. And so essentially you get a set of linear observations of the coded bits, and there is multi-user interference, right? Except that you don't know the columns of S. You don't know which spreading sequences have been picked by the users. So now, in order to do the decoding, you have to go through 4 steps. So what we have to do first is to determine which spreading sequences are active. And you have to do this in a blind way because you haven't done any decoding yet. So first job is to find which spreading sequences are active. And once you have determined which spreading sequences are active, you can go back to this model. Now you know your S. You can compute an estimate of each one of the bits in V. And then you do the decoding using a polar decoder or LDPC decoder or whatever code that you have used. And then you do serial interference cancellation, right? What does serial interference cancellation means? If you're able to decode a code word, then you subtract that from the received signal, and then you do the same thing again. Okay, so this is the main idea of the decoder. And I'll walk you through one example just to make sure that we get this fully. So suppose we have 3 users in the network who are active. And let's say user 1 randomly picked a spreading sequence, and that turns out to be spreading sequence S5. Now users 2 and 3 pick spreading sequences, but maybe both of them picked S1. Okay, so there are 3 active users and 2 active spreading sequences. So what we are going to do at the first stage is you try to blindly find out which spreading sequences are active. So maybe you get an estimate that says S1 is active and 2 people transmitted S1 or picked S1. But you probably, let's say, also have false alarms. You think S3 and S9 are active, and one person picked S3 and S9, when in fact nobody actually picked S3 or S9, right? So now, assuming that this is the set of spreading sequences that are active, you form an MMSE estimate of the coded bits in your code, and then you go through the decoding. Now, if you think about what is likely to happen if you do your coding right, these users are not active, right? So essentially, you are trying to decode something when nobody actually used that spreading sequence. So if your code is right, done well, you should realize this is what's happening, and you should say that you should not be able to decode this particular user. Whereas you should be able to decode one of the users who transmitted in S1, right? So maybe you are able to decode users 2 and 3. And if you're able to decode users 2 and 3, then you subtract the combination of users 2 and 3 from the received signal. And then you try again. And when you try again, this time around, you will probably get S5 correctly. Maybe you still get some false alarms, S3 and S15. But again, you rely on the code to tell you that these users are not present in the system. And that's basically how you finish doing the decoding. Okay, so now the rest of the thing that remains to be shown is to show that these 4 things that we have to do.
In the previous example, you walked us through where did the fading channel figure into this, if you want to consider that?
Really? Okay, really good question. I did simplify things without putting the fading channel in there, but it will. So if you have a fading channel, you still have to do the spreading sequence detection blindly. Now, once you do the spreading sequence detection blindly, assuming that you have your spreading sequence is correct, you will need pilots. You will need pilots to estimate the channel, and then using those estimates, you will have to form estimates of the coded bits and then subtract them.
Okay, got it. Thank you.
But it is a valid point. I think Chandra raises a very good point, because typically in these problems, we are operating at very, very low SNRs and with a lot of multi-user interference. One substantial difference between this multi-user problem and things that people have studied in the past in CDMA, for example, is that K is much larger than what we are used to. I think somebody has their mic on. Joy, I think, has their mic on.
Sorry, can I ask a question?
Absolutely.
Okay, so I was wondering that this iteration 1, the choice that you have made, that's the blind choice of the spreading sequence. So that is chosen completely at random?
No. The choice is not blind. The detection algorithm is blind. Blind means that I don't know the transmitted code word. It doesn't mean that I blindly pick some things. So blind basically means this. So what we do is this: for each spreading sequence, we compute a statistic. The statistic is essentially, you take your received vector, you correlate it with this spreading sequence, and then you look at the magnitude squared of that. The reason I call this blind is that notice that this, by squaring this, I'm essentially removing the modulation. I'm not assuming whether I know that the transmitted bits are +1s or -1s. That's why I call it blind. Okay.
So it means that if I have hit upon the right set of spreading sequences, this metric will be high.
Yes, correct.
Okay. All right.
So typically what happens is, depending on your SNR, you get a fraction of them correctly at first. And then once you iterate, you start to get more and more of them right.
Okay. All right. Thank you.
Okay. So I think in the interest of time, I'm going to skip many of the details. I will just, okay. So I'll tell you. So then what needs to be done to show that this thing works is you have to show that there are 4 ways in which this can fail. And then you can pick the parameters carefully enough to make sure that the probability of each one of these things becomes small, right? So the first thing that can happen is multiple users can pick the same spreading sequence to a point that your code is not able to decode them. So what we do is we pick the parameters in such a way that the probability of 2 people picking the same spreading sequence vanishes as N and K become large. The second thing that can happen is that the sequence detector can misclassify a spreading sequence as inactive. Somebody actually chose spreading sequence 1, you thought it was not there. The third thing that can happen is that your code can tell you that some sequence was decoded when in fact that person did not transmit at all, right? And finally, what you can have is a false alarm. Nobody picked a spreading sequence, but your blind spreading sequence detector thinks that somebody picked that spreading sequence, and your code gives you a valid code word based on that spreading sequence. And you have to show that all 4 of these can be made small. And I will just very quickly show you something I feel which is quite nice and insightful. So the way to make these things small is to pick the 3 parameters that you can carefully. So the 3 parameters you have are the following: the total number of spreading sequences in the master list, right? So what you want to do is you want to pick this to be a constant times the number of users. And that constant typically is large, but if you pick it to be a constant, then you can use a standard balls and bins argument to show that you can bring the probability that 2 people picking the same sequence to be below whatever threshold that you have chosen. The second thing, so and notice this, when you pick a spreading sequence, essentially what you are doing is you are conveying log k bits of information through your choice of the spreading sequence, right? It's actually log k bits. So what we are really doing is this: we are taking the k non-zero indices. Each index has a binary representation of length log n, right? That log n is split into log k bits, which are conveyed by choosing the spreading sequence. And the other log n over k bits are encoded by your code. It's polar code or LDPC code or whatever. The rate of that code, however, is constant. It does not depend on k. You don't have to scale things as a function of k. And the reason you can do this is that you choose your spreading sequence length to be linearly dependent on the number of users. So then what happens is this: the spreading sequence length increases as the number of users increases. And this puts you in a regime where the minimum mean squared error does not scale with k so it converges to something. So as far as the code is concerned, every bit in the code, it's as though this was transmitted through a Gaussian channel with a fixed SNR. This SNR you can compute, but it's not changing as k changes. And that's what makes the whole thing work. And I know that I'm over time, but I will quickly show you 3 results on this. So the first thing is this. So if we use this algorithm and then we constructed a compressed sensing algorithm to compare ourselves to this Gaspar and Reeves result that I mentioned before. So this is the performance of the polar coding scheme. And this is the performance of AMP with MMSE as the recovery algorithm. Now, the complexity of AMP MMSE is at least order of n times m. N is the dimension of the sparse vector, m is the number of observations that you have. Whereas the complexity of this is more or less independent of n. It depends only on k, the sparsity. So the big difference between these two is in the complexity. Of course, the performance is slightly worse than using a Gaussian random matrix with an AMP MMSE. And so here is an example from federated learning. So in this case, what you're trying to do is you have multiple users. They're trying to train a neural network to solve the CFAR10 classification problem. The network itself has 270,000 parameters. So dimension is 270,000. You sparsify the gradient by picking only 270 entries out of, so 1% of the entries. And you have 8 users in the network. So the 8 users are trying to train. So the sparsity becomes roughly 270 times 8. And the 3 plots here show what happens if you did no compression at all. So that is the dense vector. So if you could transmit the gradient exactly every time. And these are the performance of using this polar code based compressed sensing, assuming that you had so with noise and without noise, and the point I want to make is this. So this is the actual testing accuracy of doing the classification after training the network, and you can see that there is almost no difference between sending the dense gradient vector and sparsifying it and compressing it using this federated learning kind of approach. The last thing I will show is performance for heavy hitters. So in heavy hitters, so here is the performance comparison between using this polar coding based compressed sensing scheme to chaining pursuit. Chaining pursuit is an algorithm that came from the theoretical CS community. This is very popular in heavy hitters. So in this problem, n is 2 to the 64. You're looking at 64-bit IP addresses. There are 25 heavy hitters. So here there is no noise in the observation per se, but the vector that you are sensing is not exactly sparse. And so it's like, 40% of the users are heavy hitters and 60% of them are not heavy hitters. And what is plotted here is the best. So when you try to form the sketch and then you recover who the heavy hitters are, and we're looking at the error between the true heavy hitters and what the reconstruction error is. And you can see that there is a huge difference in the number of measurements that you require for the same. In fact, over the entire range we simulated, it looks like the polar coding scheme is doing substantially better than the chaining pursuit. The polar coding scheme here is slightly more complicated than the chaining pursuit. But okay, so I think I'm over time, so I will stop here. I think this is this is basically, I hope I convinced you for these 4 things that I said that I was going to convince you of in the beginning, that unsourced random access is the same as an approximate support recovery problem. And then there are interesting problems where the dimensions are very large, for which you need low complexity solutions. And communication theory or coding theory based constructions of these sensing matrices and recovery algorithms are useful, particularly for designing low complexity algorithms. So I will just leave with the last thought saying, so now that this polar coding scheme seems to work well for the single antenna case, we have some recent results for multiple antennas. So if you take this viewpoint, then you can go back to the multiple measurement vector problem for large N. And we are working on this. Hopefully we hope to show that this works well for these large scale multiple measurement vector problems. I think I'll stop here. Be happy to answer any questions.
Yeah, hi Krishna.
Yes, hi Chandra.
Hi. Just 2 quick questions. One is I didn't fully follow why it is approximate support recovery and why it is not equivalent to an exact support recovery problem. And the second is, would you comment on connections between this and index coding, which also is quite popular in the literature?
Okay, so the first one actually is a good point. The first one is mainly because of the way the problem is set up. So when the unsourced problem is set up, the metric of interest is per user probability of error, right? So per user probability of, okay, so it is a choice to set up the metric to be a per user probability of error. So let me be clear. So that means I'm interested only in the probability with which a particular user is not recovered, and I want it to be 5%, for example.
Mm-hmm.
The reason to set the probability of error to be this way is so that I think you can get the finite block length bound to be meaningful. If you ask for, so the thing is in this, if you think about IoT, typically you are not interested in the asymptotic regime, right? So you're interested only in the small n regime. So asking for a vanishingly small probability of error, I think becomes infeasible. But it's a very good point that there is nothing fundamental in saying that this is actually the approximate support recovery problem. I think I perhaps did not use the right words. I didn't say this right. the way the problem has been set up by Yuri corresponds to the approximate support recovery problem. And I think it's meaningful. That's what I meant.
Okay. Yeah.
But it's a good point.
Index coding.
I do not know anything about index coding.
Okay, fine.
Is there sparsity in index coding typically?
Yeah. Finally, if you're doing index coding also, so for example, if you're considering generalized space shift keying, where the way you convey data bits is to activate a subset of antennas, and which subset you're activating depends on the data bits you're trying to send.
I see.
Then basically you can construct a matrix consisting of the channels between all the antennas and your receiver, and you want to know which subset of columns are actually active. And that tells you the data bits that are being transmitted. And there are many, lots of literature on it with many different flavors and so on.
Thank you. I learned something. Hopefully some of this can be applied there. I didn't know about this.
Okay. Thank you.
Sri Krishna here.
Yes.
In this, your receiver, the sparse recovery is basically happening in the signature detection part.
Exactly.
And it is like some matching pursuit or some greedy method.
Actually, that's a very good, yes, that is where the sparse recovery is happening. Beyond that, there is no sparse recovery.
But it is getting corrected by errors are getting corrected using your code.
Exactly. But I want to point out that even in the sequence detection part, the sparsity is very different from the sparsity or the original problem, right? In the original problem, no, actually, you're right. You're right. That is basically where the sparse recovery is happening. Yes, but it's true that the sparsity indices are not the same. So, for example, in my original problem, let's say I may have 1 million users, out of which 100 of them are active, right? But my spreading sequence set does not have 1 million spreading sequences to begin with. So I intentionally reduce the size of that to be something much smaller. So it's more like what you were looking at. I might pick only 2000 spreading sequences, out of which 100, I need to pick the 100 of them. So in fact, that stage is exactly the problem that you solved 2 weeks back.
Okay. Okay, thanks. Yeah, I understood.
Other questions? There is something on the chat. All right, so if there are not other questions.
Thank you, Professor Narayanan, for the engaging talk. I think there are no more questions.
If you have any questions, feel free to write to me. It's always very nice to see colleagues from all the colleagues, although I didn't see many of them. Hello to Parimal, Vijay, Utpal. Bye.
Thanks, Krishna.
Thank you.
We would like to just remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. The links have been pasted in the chat box, and the link to the recorded video will be posted on the web page as well. Thank you, everyone, and have a great evening.
Oh, hello to Anurag as well. This is wasn't expecting Anurag.
Thanks, Krishna. I forgot about the talk. I just joined. Sorry about